Please.
So from the previous equation that you wrote about the received signal, so for if we want to just have the information signal, the xt, do we just eliminate the function of n in terms of t, or do we have another expression or equation, sir?
If we want to know the just only information signal,
Yes, sir, only the message.
only the message. Only the message. And your option is, or your choice is?
Do we just eliminate the noise function, or do we have another equation?
Mm, yeah. Maybe the most correct answer, we cannot eliminate, maybe we cannot eliminate the noise totally, but we can reduce the effect of noise. For example, the power of noise usually, the signal of noise is random, but in certain period, this power is, the power of noise is constant. I hope, I mean like this. Imagine this is the noise. So noise is fluctuated, yeah, usually fluctuated. For example, this is the 0 volt. Uh, the signal of the noise is fluctuated, but usually the variance is constant, and the variance representing the power of noise. And then how to eliminate, or how to reduce the bad effect of noise? One of the most, or the best solution is amplifying the signal, so the signal component. So from this equation, I use a different color. We have to increase the power of the signal. I mean, how to increase the power of this term. This is very technical perspective. Yeah, for example, in one room, or in the class, and then there is a, yeah, for example, in the lecturing process. So in the class, there is many student and one instructor or lecturer, and then everybody talking, yeah, for example, this is just simulation, yeah. Everybody talking, student talks to the other student, and then also the lecturer simultaneously gives the lecturer. in our imagination that this room will be a lot of noise, right? A lot of noise, because there is many people speak, and then and at the end, everybody cannot hear properly what the lecturer say. I think everybody agree, yeah, because maybe yeah, because of also student talk octave, maybe there is a debate sessions, and the audience cannot hear the which one is talking, or is that the lecturer talking or not, yeah. So in this situation means that the signal and the noise power are equal. So we cannot we cannot have a benefit, right? We cannot take the information from the signal. So the solution is, if we want to how to say, if we want to point out to the lecturer should have a microphone. The microphone is a tool to increase this signal power, something like this. So it is similar. The same technique also has been used for communications. If we have a signal and the noise, how how to make the signal survive in the noise environment? We have to increase the power, or we have to reduce the noise power. Particularly, we cannot reduce the noise power. Usually, we technically, we only can increase the signal power, something like this. So there is a how to there are methods to increase the signal power. First, yeah, increasing the transmit power. Yeah, this is very easy. And then we use a low noise amplifier. Means that we amplify the signal and make the noise lower. And use a high quality device. Something like that. Is that clear, or is that answering your question, Safero?
It answers my question, sir. Thank you very
Okay.
much.
Okay. Is there any other question? No? Okay. So in here we have every notation here, the power receive, the channel, yeah, and the information, and the noise random, yeah. Usually the power of the noise characterized by the variance of the signal. And then we want to compute the capacity, yeah, capacity of the channel. So according to the Shannon theory, yeah, that the capacity is equal to the bandwidth logarithmic base 2 1 plus DSNR in term of power. Yeah, power. Yeah. So as you know that the bandwidth is just bandwidth. I mean, if we use the antenna that the bandwidth of, for example, like a Wi-Fi antenna, yeah, Wi-Fi antenna. So this Wi-Fi should works properly in 2 gigahertz, but there is a bandwidth or range. Yeah, bandwidth is a range. For example, 2.3 until 2.5 gigahertz. So something like this. So this is the bandwidth. So bandwidth is just bandwidth means that the unity of spectrum. I mean the hertz. So we can ignore being one. Mean why one? Yeah, because we can make a unity or normalize. Yeah, normalize become means that once become one. So it's mean that we have the formula become like this. So this is the capacity per hertz. So we will have the unit become bit bit per second per hertz or bps per hertz. This is the unity of the capacity. Will be how many bits per second that can be carried by 1 hertz signal. Okay, so in here we can write C equal to logarithmic base 2 1 plus the S and R is power received H2 and then the XT 2 and then N to T something like this. Remember that, so we can write like this PRX H2 this is X to T and this is we can write thing like this. Please notify this as you remember as if you remember that the power of noise equivalent to the variance of noise signal of noise signal, yeah, power of noise signal. So and then PRX H2 this is and the XT we can simplify become one means that this is the power of the information power of information become one. Oh, maybe one of you asking, why, sir? Sir, the power of information become one. Yeah, usually the information itself is embedded by the transmit power. Yeah, the information, they does have they don't have uh the physical unity. The information doesn't have a physical unity. So they have in entropy, apa, the unity of information is entropy, but entropy, they doesn't have the physical unity. So we can simplify, become one. Yeah, become one. So in this case, the capacity then depend on the power received, power noise, and the channel condition. X per power noise. This is the power signal or receive power, and then this is the power noise, and then depend on the channel. So from this expression, we can analyze that the capacity of the channel depend on the receive power by antenna, the noise power, and then depend on the channel condition. Okay, please imagine this component. Particularly when you access the Wi-Fi, yeah, when you access the Wi-Fi. It is true that when you get closer to the router access point, you will increase the quality of the image. Maybe you become smooth, better quality of the signal. I mean, the better quality of the image, and quicker download. Yeah, maybe also more no lag for conference, something like that. So it is true, because when we get closer to the uh, router access point, means that we increase the receive power at our device. And also, when the noise, yeah, usually the effect of noise is particularly if we get farther to the router access point, the receive power decrease and the effect of noise getting dominant. Means that the noise power relatively constant, yeah, uh, but when the receive power decrease, and then the effect of the noise increase, something like this. And then the second, I mean the third point is the channel condition. Channel condition. Channel condition is the environment, how to the signal arrive at your smartphone or your device. The best channel condition is a relative constant. Yeah, I mean that the channel is not fluctuative. Yeah, so I said that relative constant, but this condition is very, very difficult to achieve. And then random. And then random. And when we have a random, and then this will affect to the SNR. Okay. Okay. This is just a review from last week. Is there any question? No?
No, sir.
No, okay. Okay. Uh, in this demo or in this hands-on, I will use a random channel. Random channel. With the random channel using Gaussian. Gaussian for each component. You remember that this channel is a complex channel. Complex channel means that this channel has two components, real and imaginary, and each component using Gaussian. So this is for real, and this is for complex, and then we will generate this Gaussian channel. Uh, okay. Okay, we create a Gaussian channel, and then second, we create the Rayleigh channel. Gaussian channel, just for information, Gaussian channel means that the channel, the edge is constant, constant. The noise is Gaussian. Rayleigh, Rayleigh channel, the edge is Gaussian. I mean, not the edge, but the real component Gaussian, imaginary component Gaussian, and then we have a Rayleigh channel. Okay, we will make simulations. We will make a simulation. Okay, I will show the Matlab. Okay. So I will first you can new something like this, new from this plus symbol, and then you can make you can save, for example, in document WiCom class, and then channel capacity, and this is how to naming in the Matlab. Actually, we are prohibited to use a space, so we need to become like this, become one phrase lah, or one word. Yeah. Okay, something like this. And then first we have to generate the uh what we have to set the power receive power say Rx equal to uh, 5 GPM 5 GPM so we have to do this, and sigma equal to GPM, and then the end. This is the power noise. So, for example, we have the so in case Gaussian channel means that the h is constant, that the h is constant, and then we can write the S and R become of Gaussian become PLX divided by sigma. Yeah, by sigma, but here we need to convert dPm to watt. Yeah, so we start to convert dPm to watt, and PRX is equal to remember that computing the watt to dPm 10 logarithm base 10 Rx power in watt divided by 1 watt or equal this one, then logarithmic base 10 power in watt times 3/1000. Yeah. So PRX in watt is equal to 5. So this means that f5 equals to 10 log base 2 base 10 power in watt. This is 10 by 3, and then the watt. Fine. So here the watt equals to 10 so something like this. You can find 10 power by 5. So this is power in watt. This is the so this is minus divided by this is power noise power signal power in something like this, and then H input is constant, unit constant. Unit constant means that the H is 1. And then this, and then we compute the capacity in Gaussian channel. Okay, and then C equal to log 2 logarithmic base 2. This is the S and R G, yeah, something like this. Plus 1. Plus. So here the compute capacity with the unity being bit per second per hertz. So if we compute this one, we just like this and then run. The folder. This is the capacity in terms of bit per second per hertz. Means that if a communication system has the receive power being 5 dBm and the noise power is minus 10 dBm, and then we will have a capacity to bit yeah, 2 bit per second. We can send 2 bit per second. 2 bit per second. You can imagine that 2 bit per second per hertz. For example, if we have 2 giga, for example, Wi-Fi, yeah, Wi-Fi works into 4 gigahertz, and for example, yeah, we have 10 megahertz bandwidth. The bandwidth is 10 megahertz, and then the total capacity total will be 2.5 times 10 power by 6 is around 20.5 Mbps. We can enjoy or we can use the 20 megabit per second bandwidth. Until from this simple computation, is there any question?
Yeah, I can still understand, sir. But maybe your voice is a bit small, sir.
Smaller. Oh, sorry. Wait a moment. I will set. Right now is okay.
Okay, now it's okay, sir.
Okay. If you want to plot in using a graph, for example, we variate based on the still channel capacity with Gaussian channel capacity Gaussian channel capacity with many power setting. Nah, with power setting. So yeah, we have to identify the power itself. For example, the power, let's say PRX It's directly wait a moment. I have to write compute Gaussian channel. Yeah, compute Gaussian channel. Okay, and then define the power receive. For example, we have to know specific power receive, or we variate based on the power receive. Let's say we want to compute Gaussian channel with power receive, receive power from uh, yeah, maybe from mm, from usually is uh, 0.01, yeah, until 1 milliwatt, and then we write this. We have to make an array. For example, in this case, we have to write the matrix. So, for example, from 1, 2, 3, 4. In this case, yeah. Maybe we have to spacing, make a spacing. Satu, 5, full.
Excuse me, sir. There is no sound.
Oh, no sound. Oh. Okay. Allow me to explain that the after we compute this graph, actually this graph representing the capacity in terms of bit per second per hertz, and this is the power receive in watt, in watt, yeah, in watt. For example, we point to this point, yeah, make a pointer to this point. So this point, the capacity is 3.3 bit per second per hertz. This happen when in this point when the power of signal 10 times of power noise. Okay, 10 times. And this point when the power signal 1000 times of the power noise. You can see here the capacity is around 10 lah ya, 9.966 bit per second. This is how the capacity, this is how the capacity increase logarithmically proportional to the power receive, given by that the noise power is 1 milliwatt. Okay, is there any question?
No, sir.
No, okay. Okay. If no, we move forward to the next simulation. We will create the capacity under Rayleigh channel. We first generate generate channel realization. Channel, yeah, channel realization means that like we simulate many channel here. Realizations. We generate the channel realization. For example, 1,000 channel realizations, because in here the channel itself is random. Yeah, random. We have first to identify the each component. So we need generate real component, and later we will generate the imaginary component in phase or quadrature, ya, in phase or quadrature. Yeah. So in phase, let's say the in phase HI in phase radio is the normal, ya, normal Gaussian. My left nor random. The mu is 0, sigma is 1. Oh, I need the statistic. Don't 0.1. Is it correct? Okay, I can generate this like this. is generate uh, okay, is this one? Okay, maybe we can skip this. If you remember that if the channel has two components, real and imaginary, and each real and imaginary follow the normal random, let's say the normal random, and this will have the distribution of age being the exponential distribution of h power by 2 all. This is a power of the channel. Exponential distribution. So we can wait a moment. I will generate the exponential random variable. Exponential random. In this case, requires status machine learning. I will try to use another computer that install Scilab. Generation. Maybe I can use this one. 0.1 normal. Okay. Okay, seems to be okay. I will stop setting this one and then I will connect the to the Zoom, my other computer. ID is 87107876561. Passwordnya 5466952. Okay, got it. This now, and then participant setting. Okay. Okay, I will show you the emas. I will share screen. Yeah, biar everybody can see. Okay. This is the Scilab, and then I will actually why I fail using Matlab because I cannot generate random variable, normal random variable. Yeah, as you maybe you can see that to use the general Gaussian random variable, the Matlab require the statistical toolbox. So it's mean that it's not installed in my Matlab yet. Okay. Here I will generate the in phase and quadrature component. So in here, HI, this is in phase component. Better to say, yeah, let's say create WiCom class. Yes. And then capacity Rayleigh channel. Okay, HI is in phase component, and then I will generate random with the mu being 0 and the standard deviation being 0.5, and then no, wait a moment. Oh, okay. So This is 1000 realizations using normal, ya, normal, something like this. And then this. So the quadrature become random, 1000 realization, and this is also normal. This is the quadrature component, and then oh, I don't know, it's a bit different. Okay, let's try to run either no define variable in line 1. Something like this maybe better. Save and execute. Okay, seems to be okay. Okay. So H become E. No, not I. 0.5 times E plus E times 0.5 times E. Not high. HQ, yeah, HQ, yeah, something like this. Yeah, actually it's similar, but it should be E times something like this. So in here we no need to do this one. Or maybe we can use this. Itself undefined hub. At line 1. Loh, apa ini? Hey, this one is correct. Hmm. Lah, sebagai undefined variable age. Oh, hmm. Oh, persen ya. Ah, sorry. Bisa. Oh, it should be. Okay, good. So in here we comment. Huh? Comment silent. Oh, okay. Generate Rayleigh wedding channel. And then the and then for the power is still similar with the Matlab. So this one. So this is the generate Rayleigh wedding channel, and then the power Rx still same ya. Eh, 1, 5, 10, 50, 100 dibagi 100. This is receive power. This is receive power, and then this is the sigma equal to 10 power by minus 3 ya, berarti it means that this is equal to receive power power noise ya, receive power noise equal to 1 milliwatt ya, and then this is receive power from 0.00 until 1 watt with this space, and then we compute the SNR. So and then we after we generate the fading channel, and then we compute the channel power or channel gain. Actually the power is the power h power h, actually h times the its conjugate, conjugate in Scilab. So conjugate function conjugate. Okay, so it's conjugate of h, conjugate of h, and then the mean power. So we have to compute the mean power. The mean so power of h become singular. So mean of pH, it's what? Mean or average, yeah. Okay, let's try. Let's try. Where is the H, min H, bisa nggak? Oh, bisa. Oke, conjugate H bisa. Conjugate, oke. So H kali conjugate dari H. Aduh, kok nggak bisa ya? Gini ya. Aduh, nggak bisa nih. Mana dong? Okay, it's work. So it should be multiple by this one. This one, okay. Misal pH itu sama dengan H kali conjugate H. Oke, dikasih min aja langsung. Nah. Oke. Okay, and then we want to compute the SNR. SNR, so we have to compute the PRX, correct ya? Coba ini dihitung dulu deh, dicek. Okay, it's work. PRX dikali PH dibagi sigma. Yes. And then plot PRX, comma, and then compute the capacity. Log base 2, log base 2, 1 plus SNR. Yes. And then this is C. Is that? Then save and execute. Okay. Let's compare. So, and then, so, without times PH. Hold on. This is C2. Ini log basis 2. 1 plus SN. Nah. 1 P RX bagi sigma. Hold on. Plot PRX, C2. Plot in. Clarity plot. Ini bisa nggak sih? bisa dihitung. Okay, so I have to save ya. Export aja deh. Export to file. Jenis filenya apa? PDF. PDF. My document. And WiCom class. This is channel capacity. Channel capacity in Rayleigh environment. Okay, ya pot landscape aja deh. Okay, okay, that's all. For the explanation of this graph is similar to the Gaussian, but thing that I want to show you is the performance capacity. Let's compare. Here I will send this file to another my computer. Wait a moment. So this is become class. So I need to email this one. I need to synchronize. I want to open my email, Gmail, and then I send this one to okay, and then this one and this one send to send to my email as well, and then okay, I send without text body, but the file I hope is already sent. Okay, let's check stop share, and then I open in my other computer and Gmail. Uh, maybe it's better to WiCom. Where is my WiCom? Then so this one, and view. I need to rotate. Mana sih rotate? Rotate. Ah, ah. Uh, uh, and this one, okay, good. Maybe for this one, it should be smaller. Okay, you can see here. Okay, allow me to show you something. And this one for the first screen, yes, first screen. Okay. Okay, sorry for making you a bit uh yeah, maybe wasting time about wasting time for writing me. Okay, allow me to explain. this is the capacity in Gaussian channel. This is capacity in Rayleigh channel. Okay, and you can see here the graph is maybe the pattern is similar, but please take a look for the capacity performance. This is the capacity. Capacity, the unit is bit per second per hertz. Also, it is similar. This is the capacity, bit per second per hertz. This is the power, and this is the power. Okay, you can see here the capacity increase for both channel. Yeah, when the power increase, the power receive increase. But you can see here, please take a look for the last point here. The last point, when the power received is 1 watt, as well as for this scenario, but the capacity you see here, there is a gap here. Means that the in relay environment, the capacity we will have a decreased capacity compared to the Gaussian channel. Or in another word, we can see here in more worse scenario, I mean in worse environment conditions, particularly the capacity decrease. Yeah, you can see here, this is around 10 and become 9. This is 10. If we have a Gaussian channel, we have 10, but if we send the transmission in Rayleigh channel, we got only 9 bps. Maybe in this scenario, I mean, per hertz is not so big deal. Only 1 bit, yeah. It doesn't matter 1 bit. But if this is multiply with the 10 megahertz bandwidth, it will be matter. It will be matter. So the point that I want to point, the point that I want to underline is the channel condition is important, and then the channel condition is depend on the environment, environment, environment. Yes, depend on the environment. So as the telecommunication engineer, we should properly design the communication system in a way that the signal propagate with the constant power. If you can maintain the signal power being constant, it is a good, it is a good point. Because from the fact, this is the real happen. At least from the simulation and analytical perspective. So yeah, that's all my demo. So we already simulate that the capacity is depend on the receive power, depend on the channel condition, and depend on the noise power. As engineer, it is important to design, yeah, a good system communication by considering the channel condition. This channel condition we will have from the environment where the system device is set up. Okay, that's all our class today. Is there any question?
No, sir.
No. Okay. Thank you very much for your attention. And next week we move forward into subtopic. Yeah. Next subtopic. If I'm not mistaken, I will check. Maybe next week we will discuss about the MIMO in wireless communication. Capacity linear modulation. Oh, no MIMO yet. Okay. Flat fading channel linear modulations. Okay. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh, and see you next week.
Thank you very much,
Thank
sir.
you very much, sir.
Waalaikumsalam warahmatullahi wabarakatuh.
See you next
Thank you
week.
very